Hi, I'm Simon from TU Munich. I'm very glad to present our ECCV paper, Power Variable Projection for Initialization-Free Large-Scale Bundle Adjustment. The bundle adjustment problem refers to the joint estimation of camera parameters and 3D landmark positions. A good initialization is required for most BA solvers. However, the underexplored variable projection algorithm exhibits a wide convergence basin even without initialization. In our paper, we are the first to address the scalability of initialization-free BA problem. In practice, we extend a recent inverse expansion technique linked to power series to the VarPro algorithm on one hand and to Riemannian manifold optimization on the other hand. That leads to significant improvements in terms of speed and accuracy. Let's formalize our problem. The goal objective is to minimize the reprojection error over camera parameters and landmark positions. It is a classical problem with a good initialization. However, the case without initialization is very uncharted. It can have a huge impact for structure from motion or SLAM algorithm. Recently, a new line of works has attempted to solve a stratified BA problem. It is composed in two minimization problems, step 1 and step 2, followed by a metric upgrade stage. In this work, we focus on the first two stages. The first step models the camera as a projective one. As the initialization is randomized, Hyeong 2018, that we extensively follow, use the VarPro algorithm. The second step refines the camera parameters and the landmark positions obtained with the first step. Very few solvers have been designed for efficiently solving VarPro. Most of existing works use a direct factorization that is poorly scalable. Let's formalize the first minimization problem with xp the camera parameters and xl the landmark coordinates. It can be written as a separable nonlinear problem. Due to the separability of the equation, a closed-form solution for optimal landmark coordinates is straightforward. The dagger corresponds to pseudo-inverse. We substitute the solution for landmarks and we get the following reduced problem. An approximation of the Jacobians, called RW2 approximation, leads to the following normal equation. We use the show complement trick to reduce the size of the problem. If we compare with the traditional LM algorithm, the only difference is the landmark damping V lambda. This minor change leads to very different convergence behavior. Let's recall the inverse expansion method proposed in our CVPR paper, Power Bundle Adjustment. In practice, this theorem can be applied to our undamped show complement. Let's factorize the show complement by U lambda and let's take the inverse. The first block can be expanded into a power series. By applying it to the right-hand side, we can get the camera parameters and then the landmark positions. We compare our solver PoVar to PoBA, to the direct Cholesky factorization used in the POS paper, and to VarPro solved with the PCG algorithm. We use the BAL dataset and we plot the performance profile for 3 different tolerances. Both inverse expansion solvers PoVar and PoBA are very competitive for the largest tolerance, and PoVar clearly outperforms its competitors for the smallest tolerance. Let's analyze the second step of the stratified BA strategy. As the coordinates are homogeneous, we project onto the tangent space of xp/xl and we use traditional LM algorithm. That leads to the projected normal equation with inhomogeneous unknowns delta xp and delta xl. We use simpler notation and the show complement trick on the tangent space. Similarly, the eigenvalues of the following matrix are smaller than 1. We can expand the show complement into a power series and get the post parameters and the landmark coordinates. Finally, we backproject to get the homogeneous updates. We call this method Riemannian for BA. We compare the combinations of our two solvers for the two steps of the stratified BA in blue on the performance profiles. Our solvers clearly outperform their competitors for the BAL datasets for all tolerances. In conclusion, we have addressed the scalability of initialization-free BA problem. We have extended a recent inverse expansion method to the VarPro algorithm and to Riemannian manifold optimization. That leads to significant improvements in terms of speed and accuracy. Last but not least, let's highlight that the BA problem without initialization remains largely uncharted, and lots of improvements can still be done.